Hi everyone, here we are again starting a new unit. We continue from in the same topic, which is convergence, but now we're going to do a specific type of convergence, which is the law of large numbers. And we start with the cases when we have second and fourth moments. First, law of large numbers is something we have already seen in previous modules, and it's something at the heart of probability and statistics, and in some sense it even justifies the definition of probability as with a frequentist approach, which says if we have a sequence of random variables, x1, x2, x3, etc., and you can think these random variables can be just representing success or failure in a certain random experiment that we repeat again and again and again. And each time we repeat, we are changing the index here, x sub 1, x sub 2, x sub 3, etc. And then what we see is if we count and we add together the effect of these random variables, so up to n, for some very large number n, and if we divide this by n, this should converge to the expectation of these random variables. This is the formulation when these random variables all have the same distribution, so they all have the same expectation, and this is why we write here for expectation, we write the expectation of x1. In more generality, we can have random variables that do not necessarily have the same distribution, and in that case we cannot say it converges to a common expectation. Maybe they don't have all the same expectation. In that case, what we can write much more generally is we take out the expectation of these random variables and divide that by n, and then we have that altogether converges to 0. And now there's something here that we need to specify, because what is on the left here is random, because even though these are just numbers and this n is just a number, these are random variables. And this is why law of large numbers appears in this chapter. It is, we have to specify how is it, in which sense does it converge to 0. And well, there are two senses, or the two most common senses in which random variables will converge to 0, which, well, technically is a random variable. It can be almost sure, or it can be improbability. And these two different interpretations for the law of large numbers, or these two different versions of the law of large numbers, are called strong law of large numbers or weak law of large numbers. And to simplify the notation, we're going to write Sn to denote this partial sum of random variables from the first one, second one, up to the nth one. So law of large numbers really becomes just saying Sn minus the expectation of Sn divided by n converges to 0. And again, it can converge almost surely, and that will be the strong law of large numbers, or it can converge in probability, and that will be the weak law of large numbers. Now here we have the first theorem. It is called Chebyshev's law of large numbers, and it does not assume random variables to be independent, does not assume random variables to have the same distribution. So this is quite a useful law of large numbers in many contexts. It just assumes that for each pair of random variables, their covariance is 0. Of course, in order to talk about covariance, they all have to be integrable. So integrable is implicit in the statement here of the theorem. They need to be integrable also for us to define their variance. So what the theorem asks, at least in this formulation, is that the variance of these random variables to be bounded. So their supremum being finite means there exists a finite number so that they're all less than that number. And then in that case, this sequence of random variables, which again does not need to be independent, does not need to be, it can be 2 by 2 independent, that's enough to conclude that the covariance is 0, 2 by 2, which is different from the random variables altogether being independent. And the theorem says it satisfies the weak law of large numbers. And when we say something satisfies the weak law of large numbers, what we mean is exactly that Sn minus the expectation of Sn divided by n, this converges as n goes to infinity, this converges to 0 in probability. Let us move on to the proof of Chebyshev's weak law of large numbers to conclude this first part of the video lecture. As we can see, the proof is not very complicated. We use Chebyshev's inequality because what does it mean to say that some random variable, this is the random variable, does it mean to say that it converges to 0 in probability? Well, the very definition of convergence in probability is that when we look at the probability that this number is larger than epsilon, that this has to tends to 0 for every positive epsilon. So we can start by saying let epsilon be a positive number, and now we apply Chebyshev's inequality to this random variable, but the Chebyshev's inequality, the version of it that includes variance. So it will be the variance of this random variable divided by the square of this number. And if epsilon is very small, the square of this number in the denominator becomes very large, but that does not matter, that does not play any role in the argument. So now we have the variance of Sn over n. Well, we know properties, algebraic properties of variance. We have some 1 over n here, which is just a number multiplying a random variable, which is Sn. We know what happens when that number comes out of the variance. It comes out squared. So we got here where we have a variance of Sn in the numerator, and we have n squared in the denominator. This is just taking n out here as this property. So we got this inequality, and again the first inequality is just Chebyshev's inequality. And now we know what is the variance of a sum of random variables. The variance of a sum of random variables equals the sum of the variances plus the sum of the covariances, 2 by 2. However, let us go back here. We are assuming the covariances to be 0. So the covariances being 0, all we have to sum is the variances. So this identity here, so this equal, this identity here is just we are throwing away the covariances because we are assuming they are 0. And now what is the other assumption of the theorem that we're going to use? Well, for each I fixed, this variance here is bounded from above by the supremum of the variances. So each term in this sum is bounded by this number. So the sum altogether will be bounded by n times this number. And now what happens to this n here? Well, this n here will be beaten by the n squared in the denominator. Or we can say it differently. We can cross out this n and cross out the square. And this tends to 0 as n tends to infinity. And doesn't matter how small epsilon is fixed during this argument. The definition of convergence in probability is for each epsilon fixed, this limit here must hold, and this is what we have just checked. So this proves Chebyshev's law of large numbers and conclude the first part of this video lecture.